Servus and good morning from Munich. It's our last day of the Digital WE Days and we are glad that you are here. Today we are streaming live from our office in Munich and next to me you can see Frank Gräber and Maria Cuesta Martin. Frank is a field application engineer and Maria is a product manager, both for our departments EMC Shielding and Thermal Materials, as well as Electromechanical Solutions. Today the two of them will present you the webinar Thermal Management in Electronic Design. Material choice affects signal behavior, but how do you combine theory, simulation and measurements to make the right call? Let's find out. The stage is yours.
So Doreen, thank you very much for the introduction. Let's start. So for today, Maria and me are very happy that you are joining the Digital WE Days, especially our topic, the thermal management. So warm welcome from our side. Let's start into the topic with a view of our agenda for the next half hour. We start with the topic why cool and the so-called problem statement. This is my part, followed by heat transfer and stakeholders presented by Maria. The last topic is a little thermal workshop. Within this, we are calculating an example and show you the practical values with a thermal camera. So, why cool? The most device failures are because of the temperature issues. It's over the half of all issues. Together with vibration, dust and humidity, we got our mechanical stress failure. With various expansions, we get barrel cracks, inner layer cracks, corner cracks. Please have a look in the note in the top that every 10 degrees, the temperature of a component decrease, we double its lifetime. Why should you as a designer take care about the thermal design? It's because of miniaturization and the power density. This power density grows up to nearly double when we compare ZX from the 80s and the BeagleBone from the 2010s. And with this miniaturization and power density from today, for a developer, it is most of the time not possible to have the best layout according to thermal criteria. Most of the time, the developer must use the layout you see in the right hands, the best layout according to electronic criteria. This is the reason why thermal management is so important. And when is the best time to have a look at the thermal management? Directly in the beginning of the design process, because then you have the most cost effectiveness. If you detect a temperature issue during your test phase, or perhaps sometimes during your manufacturing process, most of the time you must do a design change, and this is more cost intensive. So Maria, it's your time.
Okay, so the first step in our journey is to actually realize that cooling down our devices is important. But the second question that came up to our minds is, okay, how we can actually cool down our devices, how we can transfer this heat from one point to another. So first of all is understanding that heat is an energy, so it cannot be magically created or destroyed, unfortunately, but we can play, let's say like that, with this heat and transfer this energy thanks to temperature difference. This concept of temperature difference, we will repeat it during the presentation, and I think it's important we keep it in mind. So how can we actually transfer this heat? We have three main ways. First, we have conduction, that is when we have two surfaces together that are at different temperature. Then we have convection, that maybe I have a hot component and then I have a fluid. Normally this fluid is air. And last, we have radiation. We don't talk a lot normally when talking about thermal management about radiation, but it's an important topic that we will also cover in the next slides. So, talking about conduction, when I'm having two surfaces together, for example, a CPU and a heatsink, these two surfaces are conducting heat from your hot component of the device to the cooling device you decide. In this case, for example, a heatsink. So if you take a look in the formula that you are seeing here, you can see the tips of what we have to look into when thinking about conduction. So first, we have to take into account the temperature difference. This is key. If my CPU is at 100 degrees and my heatsink is at 100 degrees, no heat transfer is going to happen. Then the contact area. If you see the little kid in the picture, if not the same, if these little kids touch just the oven with a finger or with the whole hand. The bigger the area of contact, the more conduction you are going to have. This is why normally bigger heat sinks or bigger cooling devices have more area of contact, and this is why they cool down better the devices. Later we will see exactly examples. And then we have thickness. The thickness is the gap that is between my CPU, my hot component, and my heatsink or my cooling device. So if I have just a few millimeters or even microns of air gap, then almost all the heat can be easily transferred. But if I'm adding layers, 5 millimeters, 10 millimeters, then it's going to be much more difficult. And then we have thermal conductivity. Thermal conductivity, the theory says that is the ability of a material to transfer the heat. That means that a glove of the kitchen will have really low thermal conductivity because the purpose of this material is to isolate your hand from any hot component. But for example, our thermal interface material will look for really high thermal conductivity because we want to make it easy. We want to make a really good path for the heat to transfer from our device to the ambient. Then we have convection. Convection is not two surfaces together, but maybe my PCB and a fluid. This normally is a fan. So when you are working 2 hours in the computer and suddenly your fan starts working, is because the computer realized, oh, I'm heating up, let's cool it down with cold air. So again, in the formula, we realize that temperature difference is present. If we are sending hot air to our component, then no heat transfer is going to happen. It should be a temperature difference between both things. Then we will have the area available. If I choose a really small fan, in this case, for example, and it's only affecting part of my PCB, then probably the heat transfer is going to be limited in comparison to including 2-3 fans or a bigger fan that affects my whole PCB. This also, it's a compromise that the designer has to have when designing their device. And then we have a convection coefficient that is a value that we should decide depending on the situation. If, for example, in this case, we have a couple of PCBs and there is no fan, then the value normally we consider it 1. If we include a fan, depending on the characteristics and everything, we can increase this value by 5, 10 times, it depends. And if we are in vacuum conditions, probably this value will be 0, so no fans in the aerospace applications because no air is moving around the device. But again, as a common factors as the previous formula, temperature difference and area available is key. And at the end, we have radiation. All bodies at some point radiate, so the table, the computer, ourselves can radiate some heat, but how we can enhance this radiation? First, temperature difference. Again, if we are the ambient and my body is at the same temperature, I'm not radiating any heat. Then we have 2 factors that I'm not going to go into detail, but geometric factor, Boltzmann's constant, and then again, the area available. If I have a really small component, it will radiate less than a bigger component just because the area available is bigger. So area available and temperature difference, again, is a common factor. And then we have emissivity. That, again, as a theoretical explanation, is the ability of a material, of a body to radiate the heat. How easy is to radiate this heat? And maybe you have never thought about it, or yes, but you go into searching for a heatsink for your application. And then you see that you have several options, several designs. Some of them are made in polished aluminum, some of them are black anodized. Why this different? Why we are anodizing, for example, devices like heatsinks? Because polished aluminum, if you see it in the corner, the value of emissivity is almost 0, 0.04. But if you take the same value with anodized aluminum, the value is almost 1, it's 0.9. So you can see that this emissivity factor is taken into account when we are, for example, choosing a heatsink device. Okay, now we can go a little bit deeper. We know that it's important to cool down. We know that it's important to know how to cool down our devices. And then we can go in deep of the stakeholders that any electronic design should face when designing any device. We have different steps, let's say like that. So the first step is the PCB level. Any engineer that is designing to start a design of a PCB will say, okay, how I do my layout. First of all, we have to understand the components that we are including it. In the past, almost all components were THT, so these components with 2 fingers or 2 legs that are soldered to the PCB, but that has not direct contact with the PCB. So almost all the heat is concentrated in the component, and then it's sent to the ambient with more or less problems. And then we are now going more for SMG components. These components are smaller, so it should, like my colleague Franz has said, this miniaturization enhance this challenge of thermal management, because also you are increasing the power that you are putting the component, increasing or decreasing the size of the component. But it's true that this component is directly attached to the PCB. So all the heat flow, or 80-90% of these heat flows, can, instead of going to the ambient, go to the PCB. And then you can use this PCB to transfer the heat and to have much bigger area of contact. We have included a formula that is a first approach when you are doing your design, that is a temperature junction formula. At which temperature my component is going to be when I turn on my device. You have to know the temperature ambient. Yeah, I always say, Frank, it's not the same. I'm from Spain. It's not the same to be at 40 degrees in Spain than at 10 degrees in Germany. So this is important. Then we have the power that you are going to dissipate. This can be the same in Spain and in Germany. And then the resistance junction to ambient, that normally it's included in the datasheet of the component. So again, simulations or real-time applications, it's the most suitable approach, but sometimes to have a first contact of this value and to have a first idea of what temperature is achieving my component can really help us in our design. Then is the placement, okay, how you are going to distribute these components. The ideal case is just one component in the middle of a big PCB. Unfortunately, I think it's not the case for almost any device in the industry right now. So we are adding complexity, we are adding components, and depends of how we lay out these components, this is going to affect the thermal management. In this presentation, we cannot go in deep. We can be talking ages about this, but basically what we want to make you understand is that any decision that you make when designing a PCB is going to affect the thermal performance. It's not magic. It's not, oh, randomly this is happening. So you have in your hands the power to play with these values and to help to have a really good thermal management approach in your devices. Then, talking about thermal interface materials, this is like the contact point, no? The layout between my PCB and my cooling device. Here we put heat sinks, but can be heat pipes, can be any other cooling device that you can think about. So when we are looking about thermal interface materials, we have to take into account first the gap you need to fill. It's not the same to complete microns that to complete 10 millimeters gap. The performance you need. Again, before we were talking about thermal conductivity. The higher, the better. It is true, but we also know that thermal conductivity correlates with price and with performance. So if my application is really high demanding, then I will go for a different option. That is, my application is not that high demanding from thermal management point of view. Then we have how we are going to process from mass production point of view, and to find this optimized cost effectiveness ratio. So, what is a thermal interface material? At the end, a thermal interface material is a point of contact between a heat source, a transistor, a CPU, a battery, whatever you can think about, and your cooling assembly. Heatsink, heat pipe, water blocks, anything you can think of. And sometimes a lot of engineers come to us, hey, I have my CPU and my heatsink, I don't need a thermal interface material because then it's adding an extra layer of between them. But the reality is that materials are not manufactured in a perfect way. So when you are putting in contact two surfaces like a CPU and a heatsink, microscopical gaps of air are going to appear. And air is a really bad thermal conductor. So including a really thin, a thermal interface material that helps the contact between them is going to truly enhance your performance. Because sometimes it's a pity that you spend a lot of time and a lot of money in really good cooling devices, and then because you are not guaranteeing a good contact between them, you are not having the performance that you could have. So the thermal interface materials are to give a path between two surfaces. Again, they are a point of contact between two surfaces, but it's not something that you just apply on the component and then magically will dissipate the heat. It's not the purpose of this material, and also it's really important to take into account when we are using them. So inside our portfolio, we have three main categories: gap filling solution, heat split solution, and hybrid solutions. So inside gap filling solutions, as the name says, the purpose is to fill a gap. The first or most common known product will be TGF. TGF is a really soft self-tacky material that we have thicknesses between 0.5 up to 80 millimeters and thermal conductivities from 1 to 6 watts per meter Kelvin. So again, a lot of times this question came, hey, what is the best option for TGF? Again, it depends. Sometimes they say, no, I want the maximum thermal conductivity, 6 watts per meter Kelvin, but my design is thinking in a way that I'm having 18 millimeters of air gap. Then it's good to go for a high thermal conductivity, but the gap that you have to complete is really important. So sometimes you say, hey, let's redesign. Let's try to reduce the gap as much as possible, so you are reducing the thermal resistance this material is going to add, and then you can go maybe to the 6 watts per meter Kelvin thermal conductivity, or maybe you can go down to 3. This is why it's important to know which factors are important in order to design, so you can play with your decisions when choosing a material. These materials normally need a compression rate, so when you do this compression, then you can complete all these gaps that maybe are existing in the materials. Then we have tins. Tins is also a gap solution, but as you can see, the thickness is almost 0.2, 0.25 millimeters. So it's a really, really thin material, thinner than the TGF, and thermal conductivity between 1.6 to 3.5. So when I use TGF, when I use tins, it depends. For example, tins, if you have to screw, if you are having a high mechanical stress application, tins is a really good option to go for. But if your gap you have to fill is 1 millimeter, then this is not an option for you. You should go, for example, for TGF. Then we have PCM. PCM is the initials for phase change material, and basically it's a material that by default, let's say it like that, it's in solid state, but when it's warm up to 60, 70, 80 degrees, it changes to liquid. So in this way, you are completing even more microscopical gaps. So let's say like that, you have TGF, that minimum you have to complete 0.5 millimeters. Then you have tins that is 0.2 millimeters, even thinner. And then you have PCM, like even microscopical gaps because it goes to liquid states. It's an alternative to thermal pastes, and it's pretty interesting from the point of view of mass production, because with this material you can pre-apply it, because by default it's in solid state, not in liquid state. So this is a really good advantage, let's say like that, for this PCM material. And then we have TTT. It's not exactly a gap filler, it's more an adhesive solution, but well, we have to put it in a category. And this adhesive solution has a thermal conductivity of 1 watts per meter Kelvin. And for example, in the example you can see, you have an LED application and you have to stick it to a heatsink. Sometimes with this adhesive solution is enough to guarantee a good contact. Then we have heat spreading solution. This solution is not with the objectives of filling any gap, of guaranteeing any good contact. These solutions are focused on avoiding these hot spots. Because if you go to a CPU, maybe the CPU is 2 per 2 millimeters, but the heatsink you are including is 20 per 20. So which is actually my contact area? My contact area, if I don't use any heat spreading solution, would be just the size of the component, this 2 per 2 millimeters, that is where the heat is created, is where the heat is concentrated. But if I use this heat spreader solution, I can increase this area of contact. So we have TGS, that is a graphite foil that has a thickness of 70 microns. So with 70 microns, you are not going to complete any gap. This is why I really want to ensure that this is not a gap filling solution, this is a heat spreader solution. But for example, in the example you see, okay, I have a IGBT and I have a bigger heatsink. So with this material, this hot spot that will be the IGBT will be spread through the whole material. And why this is happening? Because it has a thermal conductivity, horizontal thermal conductivity of 1,800 watts per meter Kelvin. Again, this is the thermal conductivity inside the material. If you are taking into account the thermal conductivity through the material, this is not the value, because again, this is not a gap filler. This is a heat spread solution. I'm saying this because a lot of times Frank especially has customers that say, hey, I'm not going to use TGF, only 6 watts per meter Kelvin. I'm going to use TGS because it's 1,800. No, this is not the value through the material, it's the value inside the material. So yeah, again, both materials are really interesting. It's just to know when using each of them. And then the hybrid solutions basically is, okay, I want to fill a gap, but also I want to spread this heat. So we have TGFG. It's a foam surrounded by a graphite foil. So this foam, you can compress it and you can actually fill bigger gaps. We are not talking about microns, we are talking about millimeters. And then we have the graphite foil that will, spread the heat as a TGS. So as a summary, we came to our minds that we have 3 gap filler solutions: TGF, TINS, and PCM. It's not that something is better than other thing, it's just that some ones are more focused on each of different applications. Then we have TTT as an adhesive solution, and then we have TGS for heat spreader solution, and lastly TGFG as a combination. And maybe you came to your mind, okay, but can I use TGF to fill a gap and a TGS to spread the heat, like combine? Yeah, you can do it instead of using TGFG. The only thing that is important is that you have the tools and the understanding of for what is the purpose of each of the materials. And as a summary, we have the guidelines, the design guidelines that are on the website available. And basically these guidelines explain a little bit more in depth the materials, the applications, how they work. So it can be a really good insight if you are curious about anything of the material before using them. And I let you
Okay.
stage.
Thank you very much. So just a moment. The next topic is our thermal workshop. In our thermal workshop, we like to compare 2 different thicknesses of our thermal interface material, VE-TGF, the thermal gap filler. There are 2 cases. In blue, the thermal gap filler pad with a thickness of 1 millimeter, and in yellow, the thermal gap filler pad with a thickness of 5 millimeter. The structure, you see it right-handed, it's over there, this one. We had the hot component, a step-down converter, followed by the PCB with the thermal vias. It's colored in green. Our thermal interface material in red, and the heatsink. So what we must do first is calculate the thermal resistance of the thermal interface material. The formula for this calculation you can find in our design guidelines. We see directly that with a lower thickness, the thermal resistance is much lower. You can see it here. This is for 1 millimeter in blue, and in yellow, this for 5 millimeters. By the way, our thermal gap filler pads are now in Red Expert. When you use the values from Red Expert, you get directly the thermal impedance. It's within the compression force. When calculating with the thermal impedance, there is a slight difference. And last but not least, we also need the thermal resistance from all other components. We find this information in different data sheets. Here is an example of the thermal resistance of our hot component, and we use the parameter thermal resistance junction to case. It's the first line, and with the DPAC we get thermal resistance from 8 Kelvin per watt. All this prepared information we put now in our thermal resistance network. The network structure is left and right the same. As I said before, we want to compare 2 different thicknesses. Left hand, the thickness of 1 millimeter. You can see it over there. And right hand, the thickness of 5 millimeter over there. Beginning at the bottom with the ambient temperature, 25 degrees, almost here. And the formula you can see in the note over there. Thermal resistance multiplying by the power loss and adding the temperature of the last step. We go step by step up to the temperature of the component. Here you can see that the lower thickness, in this case of 4 millimeters, nearly double the result. You can see it in the last line in the top. In the following practical example, we have to recognize that we have a look to the heatsink. So now we need the picture from the thermal camera. Yes, right? Okay. So in the following practical example, we have to recognize that we have a look to the heatsink and not on the component with the thermal camera. So what we expect is that the heat flow on the side with the thinner material is better, and so the heatsink is getting faster, hotter than the other one. Okay, I have to start. just adjust a little bit. So, okay. And now you can see directly that the component with the thinner material is directly getting hotter than the other one. Okay. That's all from our practical exercise. And now we have to a conclusion, if you want, like this. The two cases we compare together. And the first one we have calculated 44.5 degree, and in case number 2 we have to calculate and measured 85.3 degrees. So at the end, when we have a look in the data sheet, the maximum ratings are minus 40 degrees up to 125 degrees. So all the values are inside. But remember the first sentence we said, every 10 degrees we decrease the temperature of a component, we double its lifetime. Okay, thank you. And now we are at your disposal for any questions you may have.
Thanks to both of you for your great presentation. I really liked the live demonstration. So now everyone should be able to see the handout, and let's move to our questions. I saw that we have many of them already. I think the first question is for you, Maria, but I'm not sure. It's about the product group WETGF. What is the fiberglass layer for, and does it have any effect of the thermal performance?
Yeah, well, we include this thermal layer because for a specific thickness below 2 millimeters, the material is pretty soft by itself. So you need this extra layer to have a mechanical stability, let's say it like that, for the material. So yeah, it does have an effect of the thermal performance because you are adding an extra layer, but the alternative is to not have a material below these thicknesses. So at the end, it's sometimes something we cannot avoid, but knowing that it exists and that it can have a little bit of effect, it's what matters.
Perfect. Thank you very much. Great answer. And another thing Herbert wanted to ask, it's about a different product group, I think. It's about a product group WEPCM. Our application does not reach phase-changing temperature. Will the WEPCM still work?
Do you want to say it?
Yes, I can. Yes, it will still work. But normally the big advantage of the PCM material is that we have a liquid state. And when we don't reach the liquid state, then we cannot fill microscopical gaps in the surface. And so maybe it's better to have a change, to change the material to another one, because phase changing material is big advantage is that we have a liquid state.
Perfect. Perfect. Thank you very much. So great. We already have answered 2 questions. So let's see the next one. It's from Samuel. I'm going to read it out. It's a bit longer. You can look at my screen. When an IC datasheet specifies a maximum ambient temperature, how can I verify during operation that the temperature stays below this limit? Should I measure the temperature with a thermoscope placed about 1 to 2 millimeters away from the IC, or should I make direct contact with the IC package using thermal paste?
Well,
Do you want, or
I can
both together?
Yeah. If you want to measure ambient temperature, then I will not recommend to stick it directly to the IC because the IC is going to be much higher. And even 1-2 millimeters, depends on the layout of your PCB, can still not be the ambient temperature that you are having in the whole package. So I would say it's a little bit tricky to say a final answer of where you should place it because there's thousands of designs, but my recommendation would be not directly on the IC package.
It's like this.
Yeah.
Nothing to add from my side.
Perfect. I like that you agree on this matter. That's great. So let's move on to the next question. Oh, I see we have another one related to a product. It's about a product group WETGS. What is the thermal conductivity of the WETGS in the through plane axis?
Okay. Well, in the through plane axis, we have 5 watts per meter Kelvin. It's good in the vertical direction, we can say it like this. And in the horizontal direction or through the material, we have 1800 watts per meter Kelvin. So this is a little, not a little, there's a big difference. And this is what we have to remember.
Great. Thank you very much for wrapping that up. So let's have a look. How many questions do we have left? A few more. I think we also still have time, so we can go through them. So here's one from Dennis. Oh, also about the PCM materials. When a torque is applied to components, it's supposed to cool. Does this torque still hold after the PCM liquefied, or do the screws have to be checked again?
So what do you think? I think the screws won't be checked again. Normally we have something like the feeder, something like this. And at the end, we are talking about a compression around about 10 psi,
Yeah.
something like this.
I will not say you need to recheck the component itself. At the end, the liquid material is not completely liquid. It's like a paste, let's say like that, not like water. So it will change a little bit, but not, I would say, to have to recheck the torque.
It's a little bit like honey.
Yeah, exactly.
That's the part I understood. Great, thank you very much. Okay, let's hop on to the next one from Sebastian. Oh, does the RTH junction to case specification in the datasheets refer to the entire IC case or only to the pads? Does it make sense to cool it an IC via the case without special topside cooling pads?
That's a really good question. I would say that in the datasheet you can find both, because you have the junction to ambient that normally indicates the case itself, the outside case, because it's what is in direct with the ambient, and normally it's really high. This is why normally junction to case, it's the pad side that is much low thermal resistance. So I think you can have both, if I'm not incorrect, Frank.
No, I think you're completely right.
Yeah.
The junction to ambient, most of the time we have at THT components. And in this case, most of the time we can't use these components without a heatsink
Yeah.
and thermal interface material.
And I think also it's important that sometimes it's like not that easy to see. For example, in our demo, the component is on the other part of the PCB. So what we are touching directly is the PCB, and then we have the component, because it's lower the thermal resistance from the PCB point of view than directly putting the heatsink on top of the component, because this case it's adding a lot of resistance. So also to take into account in the layout that sometimes we say, oh, directly in contact. Maybe you have a lower thermal resistance on you put in the PCB. And also the PCB can be used as a heat spreader. If you are using a copper layout, then you spread the heat directly with the PCB. So a pretty interesting question.
And the normal thing is that when you have a SMD component, you have thermal vias, and you get the heatsink on the other side from the PCB.
Yep.
Perfect. So Sebastian, I think you got the best of both of them. So let's have a look. I think we have one last question, so let's wrap it up with the question from Michael. Any special materials if you, for example, have peak power from a high power LED on a LU PCB and you need a gap filler between the LU and the heatsink?
I don't know if I understand completely correct the question, but if you are talking about not having all the same time the power consumption, then materials like PCM can be interesting, because when you are having your peak, the material will be liquid and ensuring very good contact. And then if you are having lower temperature, then it will go to solid state again. So you are having this cycling with the material, but depending on the design, also using a TGF or a heat spreader solution can be a good approach. I would say that if you need further clarification, come to us with an exact design. We give this support for sure when anyone needs to know which material from us to use.
I think it's completely right. Don't forget the formula Maria said before. The most goal, or the biggest goal, is to have the thinnest material you can get. This is the biggest goal.
Perfect. Thank you very much. I think that's all with the questions for today. if you still have any questions left, don't hesitate, contact us. Maria and Frank will be happy to answer them later for you. Thank you very much for everything.
Thanks.
I'm going to share with you the link for our digital WE days. It's our last day, but we still have a lot of interesting presentations coming until 5:30 this evening. So register again and see you at the next webinar. Bye.
Bye-bye.
Bye.